The anesthesia workstation is a system that delivers a precisely known but variable gas mixture, including anesthetizing and life-sustaining gases. It consists of an anesthesia machine, ventilator, breathing system, waste anesthetic gas disposal system, anesthetic vapor delivery system, and associated monitoring devices. Additionally, it may include a drug delivery system, suction equipment, and a data management system. The workstation integrates most of the components necessary for the administration of anesthesia into one unit. Anesthesia machines have evolved from simple inhalers to today's workstations through the integration of the anesthesia device with monitoring, alarm, and protection systems. The first anesthesia machines emerged after Morton's public demonstration in 1846. These initial devices were simple inhalers based on the evaporation of the anesthetic agent. Subsequently, more complex inhalers were developed, allowing the administration of multiple agents and the application of anesthetic flow independent of the patient's inspiratory effort. These portable gas machines were referred to as apparatuses due to their portability. Later modifications to these apparatuses led to the invention of a well-known machine called Boyle's machine, which was invented by Henry Edmund Gaskin Boyle in 1917. It incorporated most elements present in modern machines, such as high-pressure gas supplies, pressure gauges with reducing valves, flow meters, metal or glass vaporizer bottles, gas-driven ventilator, carbon dioxide absorber, and a breathing system. The individual components of this apparatus, such as vaporizers, flow meters, and breathing circuits, underwent subsequent modifications, reshaping it into an indispensable device that we now use, the modern anesthesia machine. Standards for anesthesia machines and workstations provide manufacturers with guidelines outlining minimum performance, design characteristics, and safety requirements. Over the decades, these standards have evolved to enhance the safety and versatility of these machines. The latest guidelines mandate that all modern anesthesia machines be equipped with the capability to monitor continuous breathing system pressure, exhaled tidal volume, anesthetic vapor concentration, inspired oxygen concentration, arterial oxyhemoglobin saturation, blood pressure, ECG, and oxygen supply pressure. An anesthesia workstation must feature a prioritized alarm system categorized as high, medium, and low. There are two types of anesthesia machines: continuous flow and intermittent flow machines. Continuous flow machines, which are the most widely used type, especially for general anesthesia, are designed to provide gas flow during both inspiration and expiration. Modern anesthesia machines belong to the continuous flow type. On the other hand, intermittent flow machines deliver a flow of gases only when activated by the patient's own inspiration. The Entonox apparatus, used for pain relief and sedation in dental procedures, belongs to the intermittent flow type. An anesthesia machine essentially performs three primary functions. First, it receives high-pressure compressed gas from the supply source, either a cylinder or pipeline supply. Secondly, it creates a gas mixture of known composition and flow rate using a flow meter and vaporizer adjustment. Finally, it delivers this gas mixture to the patient at a right pressure through the breathing circuit. The anesthesia machine, much like the cockpit of an airplane, integrates a lot of individual components. The labeled front and back view of the diagram summarizes these components. These components are broadly classified into electrical and pneumatic systems. The electrical system, as the name implies, deals with the electrical functions of the machine. It includes a master switch, power failure indicator, electrical outlet, circuit breakers, and data communication port. The pneumatic system deals with the pressure, which is grouped into high, intermediate, and low-pressure systems. The master switch activates both electric and pneumatic functions of the machine. It has a standby mode for quicker power-up. Most anesthesia machines are equipped with visual and audible indicators to alert anesthesia providers to the loss of main power. They are also equipped with a rechargeable battery, and it's important to verify that machines are always charged for reserve supply. Power outlets are located on the rear end of the machine and are used to power anesthesia monitoring devices. Circuit breakers located near the electrical outlet are electrical safety switches that automatically interrupt the current of an overloaded electric circuit. The data communication port allows communication between the machine, monitors, and data management systems. An anesthesia machine receives a high-pressure gas supply from either cylinders or a pipeline system and controls the gas flow to ensure a safe pressure for patients. This pneumatic function is achieved through a graded reduction of the pressure using 3 pressure-reducing zones within the anesthesia machine. These zones are high, intermediate and low-pressure systems. The high-pressure system receives gases from cylinders at high, variable pressures and then reduces them to a lower, more constant pressure suitable for use in machines. It consists of a hanger yoke assembly, check valves, pressure indicator or gauge, and pressure regulators. The high-pressure system is usually not used unless the pipeline supply is unavailable. The intermediate pressure system begins at the regulated cylinder supply pressure of 45 psi and also includes the pipeline source at 50 to 55 psi and extends till the flow control valve. It consists of pipeline inlet connection, pipeline pressure indicator or gauge, piping, gas power outlet which is not present on latest machines, master switch, oxygen failure safety device, oxygen flush, and flow control valves. The low-pressure system is located downstream of the flow control valves. The pressure in this system is slightly above the atmospheric pressure and much variable. The system contains flow meters, vaporizers and its mounting devices, hypoxia prevention safety devices that automatically regulates flow of oxygen and nitrous oxide, unidirectional valves, pressure relief devices, and common gas outlet. The high-pressure system receives gases from cylinders at high, variable pressures and then reduces them to a lower, more constant pressure suitable for use in machines. It consists of a hanger yoke assembly, check valves, pressure indicator or gauge, and pressure regulators. The high-pressure system is usually not used unless the pipeline supply is unavailable. The hanger yoke assembly is basically a structure that connects cylinders to the anesthesia machine. It performs 3 important functions: 1. Orients and supports the cylinder. 2. Ensures tight seal between cylinder and machine. 3. Ensures unidirectional gas flow. The machine standard recommends that there be at least 1 yoke for oxygen and nitrous oxide. If the machine is likely to be used in settings without the pipeline supply, it is wise to use double yoke machine especially for oxygen cylinder. The hanger yoke assembly consists of body of the yoke, retaining screw, nipple, index pins, washer or bottock seal, filter, and check valve assembly. The sketch of the hanger yoke with cylinder attached to it is shown here. The body is the portion of the yoke that attaches to the frame of the machine. It provides support to the cylinder and has a hinge that can be swung open and closed to load and unload the cylinder. The retaining screw is threaded into the back of the yoke. It presses the outlet or port of the cylinder valve tightly against the washer and the nipple when it is tightened. The conical point of the retaining screw is shaped to fit the conical depression of the cylinder. The nipple of the yoke is the inlet through which the gas enters the machine. It fits into the outlet port of the cylinder valve. If the nipple is damaged, the tight seal cannot be achieved between the yoke and the cylinder. The two index pins are situated below the nipple. It functions to prevent mounting of incorrect gas cylinders to the yoke. Specific length and positions of index pins are designed to fit the specifically positioned holes on the cylinder valves. This is called pin index safety system. The pin index safety system, or PIS for short, is a mechanism used for attaching cylinders to regulators and anesthesia machine. It involves two precise holes in the cylinder valves that perfectly align with the two pins on the receiving yoke. When these pins and holes don't align, the cylinder's port won't fit snugly into the nipple of the hanger yoke. This system was devised to prevent the inadvertent placement of a cylinder containing the wrong medical gas onto the hanger yoke of an anesthesia machine that was designed for a different gas. The positioning of the holes utilizes an arc of a circle centered around the port, with 7 hole positions equally spaced along it. Various combinations of these holes are chosen for different gases. The corresponding pins on the hanger yoke are precisely designed to fit perfectly into these holes. For example, oxygen is identified by the pin index of 2 and 5, nitrous oxide by 3 and 5, and medical air by 1 and 5. Entanox, on the other hand, is distinguished by having only the hole numbered 7, which aligns vertically beneath the center of the port. The leak-free fitting between machine and the cylinder is achieved by the use of sealing washer called Bodic seal. It is made up of non-combustible material and the metal periphery to protect its edges. Only one washer should be used between the yoke and the valve of the cylinder. Filters are placed between the cylinder and the pressure-reducing valves to prevent particulate matters from entering the machines. The check valve assembly allows the gas to enter the machine but prevents gas from exiting the machine when there are no cylinders on the yoke. The valve basically consists of a plunger that slides away from the site of greater pressure, thereby occluding the orifice through which the gas flows. In this diagram, as the gas enters the check valve assembly, it causes the valve to move away from the seat, allowing the gas to pass through. In this second diagrams, when the pressure or the flow is reversed, the valve is pushed against the seat, preventing the gas entry. In a double yoke machine, it also prevents the transfer of gas from the cylinder with high pressure to the one with low pressure for the same reason. It allows for changing the cylinder without having to unmount the in-use cylinder. While the check valve assembly serves to restrict gas flow when no cylinders are attached, it doesn't create a permanent seal for the empty yoke, potentially allowing some gas to escape. Therefore, it's advisable to always replace the yoke with a cylinder or utilize a yoke plug to prevent leaks once the cylinder is empty. The cylinder valve should always be closed when not in use. Cylinder pressure indicator displays pressure for each gases. It is located on the panel in front of the machine or near the cylinder. These indicators are called Borden gauge and should read in psi or kilopascals. A Borden gauge is a hollow metal tube made up of copper alloy bent to a curve with sealed end and linked to a clock-like mechanism. As the gas pressure within the tube increases, the tube straightens. This motion is transferred through the gear mechanism into the indicator arrow as shown. Gauges are color-coded and the name and symbol are labeled on the dial. They are placed in such a way that it's easily visible to the anesthetist. If Borden tube ruptures, gas is vented out from the back of the pressure gauge. Some machines has electronic indicators that uses light-emitting diode or LED to indicate cylinder use status and fill status. The indicator is dark when cylinders are closed, green when the cylinder is open with adequate pressure, and red with inadequate pressure. The pressure-reducing device or regulators function to maintain constant flow of gas with the changing supply pressure from the cylinder. This reduces the high and variable pressure found in the cylinder to a lower, 40 to 45 psi, suitable for use in anesthesia machines. Machine standard mandates a pressure regulator for each gases used on anesthesia machines. Pressure regulators reduce a supply or inlet pressure to a lower outlet pressure and work to maintain this outlet pressure despite fluctuations in the inlet pressure. It achieves this through a basic principle that pressure exerted by any applied force is inversely proportional to the area it acts upon. So, the output pressure of the regulator is dependent on the force exerted by the spring and the area of the diaphragm. When the inlet pressure from the cylinder is high, this will force the spring back, reducing the force exerted by spring on the diaphragm and consequently the pressure of the output. When the inlet pressure reduces, the spring will exert more pressure on the diaphragm, thereby increasing the output pressure. The output pressure is fixed by the manufacturing company and hence these are called as fixed pressure regulators. The intermediate pressure system begins at the regulated cylinder supply pressure of 45 psi and also includes the pipeline source at 50 to 55 psi and extends till the flow control valve. It consists of pipeline inlet connection, pipeline pressure indicator or gauge, piping, gas power outlet which is not present on latest machines, master switch, oxygen failure safety device, oxygen flush, and flow control valves. Pipeline inlet connection is entry point for gases from the pipeline supply. The anesthesia workstation standard requires pipeline inlet connection for oxygen and nitrous oxide. Most machines also have inlet connection for air. These connections are fitted with threaded non-interchangeable connection called diameter index safety system. This system consists of a body, nipple, and nut combination as shown. Two concentric bores, BB and CC, on the body fit into two shoulders, MM and NN, on the nipple. Only when these parts align can the threads of the nut and body engage securely. The inlet connection is fitted with a check valve like the high-pressure cylinder system to prevent reverse flow of gas from machine to the pipeline system. The pipeline also has filters the size of 100 micrometers to filter the gas. Just as the cylinder pressure indicators in high-pressure systems, pipeline pressure indicators measure pressure inside a pipeline system. It should read between 50 to 55 psig or 345 to 380 kilopascal. Pressure indicators are a requirement as per the anesthesia workstation standard. They are located in the panel in front of the machine and are color-coded and labeled with gas names. Pipeline indicators should always be checked before the use and repeatedly scanned during the use. The indicator should be located on the pipeline side of the check valve in the pipeline inlet and not downstream of the check valve. This is to ensure that the indicator reads only the pipeline pressure, as the check valve prevents the backflow of gas from the cylinder system. If the indicator was installed downstream of the check valve, the gas flow from the open cylinder would be read by the pipeline indicator until suddenly the cylinder is exhausted. Piping are pipes used to connect components inside the machine. It must be able to withstand 4 times the intended service pressure. Leaks between the pipeline inlet or cylinder pressure reducing system and the flow control valve should not exceed 25 liters per minute. If the yoke and the pressure reducing system is included, the leakage may not exceed 150 liters per minute. The pneumatic portion of the master switch is located in the intermediate pressure system downstream of the inlets for cylinder and pipeline supplies. It's the switch that controls various components of both the electric and the pneumatic system. Electrical outlet and battery charger are active when the master switch is off an electrical component, while when oxygen flush button of the pneumatic component is also independent of it and can be activated without the need to switch on the master switch. When the master switch is turned off, the pressure in the intermediate system will drop to 0. The master switch was also discussed in the electric component of the anesthesia machine. One of the serious mishaps that occurred with the early anesthesia machine was the depletion of oxygen supply that resulted in the administration of 100% anesthetic gas, leading to hypoxemia. An oxygen failure safety device and oxygen supply failure alarm are installations on anesthesia machine to make sure that the patient do not receive hypoxia gas in an event when the oxygen pressure reduces. Machine standard requires that whenever the oxygen supply pressure falls, the delivered oxygen concentration doesn't fall below 19% at common gas outlet. Different oxygen failure safety device technologies are used by different machine that controls the amount of nitrous oxide flow into the machine depending on the oxygen pressure. These are pressure sensor shutoff valve and oxygen failure protection device. The pressure sensor shutoff valve is used in machines like Datex Omeda. It operates in a threshold manner, that is, the valve is either open or shut to allow the flow of nitrous oxide depending on the pressure of the oxygen supply pressure. In the diagram A, below, oxygen pressure moves the pin and the piston up and opens the valve, allowing the flow of nitrous oxide. When the oxygen pressure falls below the preset level as depicted in diagram B, the force of valve return spring closes the valve completely. The oxygen failure protection device used in Draeger machine works on proportioning principle rather than a threshold principle, where the pressure of nitrous oxide falls in proportion of the decrease in oxygen pressure. The diagram on the right illustrates a seat nozzle assembly connected to a spring-loaded conical tapered piston that adjusts the orifice through which the nitrous oxide flow. The 2 diagram on its left shows how the pressure of nitrous oxide is reduced as the oxygen supply pressure is reduced. The total cutoff is seen at pressure less than 12 psig. The machine standard also specifies that whenever the oxygen supply pressure falls below a manufacturer-specified threshold, usually 30 psig, a medium priority alarm shall blow within 5 seconds. It should not be possible to disable this alarm. Older alarms like Ritchie's whistle used pressurized canister that is filled with oxygen when the anesthesia machine is turned on. When the oxygen pressure falls below certain value, the alarm directs the stream of oxygen through the whistle. Modern machines employ pressure-operated electric alarms, with Datex Omeda triggering at 28 psig and Draeger at 30 to 37 psig. The alarm helps preventing hypoxia caused by problems upstream in machine circuitry like disconnected oxygen hose, low oxygen pressure in pipeline and depletion of oxygen cylinder. These devices do not offer protection against a hypoxic mixture being delivered because they do not prevent anesthetic gas from flowing if there is no flow of oxygen. Equipment problems like leak, operator error like closed or partially closed valve, accidental crossover on pipeline and cylinders are not prevented by this device. Some anesthesia machine has pressure regulators in the intermediate pressure system just upstream of the flow indicators. This regulators reduces the pressure further to around 26 psi or 177 kilopascals for nitrous oxide and 14 psi or 95 kilopascals for oxygen. They ensures that the pressure of the gas supplied to the flow indicators does not fluctuate. The flow through the flow meters remains constant when the pressure remains constant. The oxygen flush, also known as emergency oxygen bypass, receives oxygen from the pipeline inlet or cylinder pressure regulator and directs a high unmetered flow directly to the common gas outlet. It is commonly labeled O2 and is mounted on the front of the machine for easy accessibility. The self-closing, color-coded flush button is commonly recessed or placed in the collar to prevent accidental activation. On anesthesia machine, the oxygen flush can be activated regardless of whether the master switch is on or off. An oxygen flush valve can provide high flows of oxygen of 35 to 75 liters per minute at a pressure of about 60 psig directly to the common gas outlet, bypassing the flow meters. It consists of a button and stem connected to spring-loaded ball. The ball is in contact with the seat. When the button is pressed, the ball is forced away from the seat, allowing the oxygen to flow through the outlet. The spring opposing the ball will close the valve when the button is not depressed. The O2 flush is commonly used to recharge the bellows in the case of a leak in the patient circuit or to rapidly purge the patient circuit of anesthetic gases in the event of an overdose of the anesthetic agent. However, there are hazards associated with the use of oxygen flush such as accidental activation which can cause dilution of anesthetics. The flush button can get stuck in on position causing barotrauma to the patient and internal leakage. These can lead to anesthesia awareness and wastage and pollution of the operation theater. Flow control valve regulates the flow of oxygen, air and other gases to the flow meter or indicators. It can either be mechanical or electronic. Current standard requires that there be one flow control for each gas and it must be adjacent to or identifiable with its flow indicator. The mechanical flow control valve consists of body, stem and seat. The stem is connected to the flow control knob. The oxygen flow control knob is larger and fluted compared to others which are rounded. These knobs are sometimes protected behind the shield to minimize accidental change in position. They are also placed high above the working surface to lessen the likelihood of contact with objects on that surface. The flow control knobs are turned counterclockwise to open the gas flow in the flow meter and clockwise to close the gas flow. When the valve is closed or the knob is turned clockwise, the pin fits into a seat of metal and no gas flows. When the stem is turned counterclockwise, then an opening is created between the pin and the seat and gas starts flowing into the flow meter. There are stops for the closed position and maximum opening position which prevent damage to the pin or disengage the stem from the valve body respectively. The low pressure system is located downstream of the flow control valves. The pressure in this system is slightly above the atmospheric pressure and much variable. The system contains flow meters, vaporizers and its mounting devices, hypoxia prevention safety devices that automatically regulates flow of oxygen and nitrous oxide, unidirectional valves, pressure relief devices, and common gas outlet. After the gases passes through the flow control valve of the intermediate pressure system, the gas is directed into the flow meters. Flow meters, also known as flow indicators, flow tubes or rotometers, indicate the rate of flow of a gas passing through them. They may be mechanical or electronic. Electronic flow meters usually have a representation of a mechanical flow meter on a screen or a number representing the flow. Flow meter is an assembly of different parts including the tube, its indicator, and the stop. The tube, known as the Thorpe tube, is contained in a chromium-plated metal casing protected by a plastic window. It is inscribed with numbers that correspond to gas flow rates. The backplate of the flow meter is luminous to allow for easy visualization. The tube is also coated with anti-static material to prevent the indicator from sticking to it. The indicator, made up of aluminum, is either a float or bobbin type. Depending on the shape and the design, bobbin type can be either rotating or non-rotating. As the valve is opened, gas flows into the tube, and the float rises within the tube until the gravitational force acting on the float is balanced by the force of gas entering the bottom of the tube. The more gas that is allowed to enter the tube, the higher the float rises within the tube. Gas passing between the float and the walls of the tube exits from the top of the flow meter and is delivered to the vaporizer or fresh gas outlet. Bobbin flow meters should be read from the top of the bobbin, while ball float types should be read from the middle of the ball. The stop, located on the top of the flow meter, prevents the indicator from plugging the outlet of the flow meter and rising to the point it cannot be seen. The other one located on the bottom of the tube prevents the indicator from falling into the inlet. There are two types of flow meters depending on the size design of the orifice. They are variable orifice flow meters and fixed orifice flow meters. Orifice or the annulus is the area between the outside of the bobbin and the inside of the gas. In fixed orifice flow meters, the pressure across the flow meter varies as the flow rate changes, whilst the pressure is constant in variable orifice flow meters. Variable orifice, synonymously known as rotometers, are the type used in modern machine. They are glass tubes with slightly smaller cross-section on bottom than the top. They are designed as single or double taper for anesthesia machine. Single taper have gradual increase in diameter from bottom to top and are used when there are different tubes for high and low flows. Dual taper have two different taper inside the same tube where the opening gradually increases from bottom to 1 liter per minute for low flow and then increases more rapidly above 1 liter per minute for high flow. So one dual taper tube can be used for both high and low flow. Flow meters adjust the proportions of medical gases received by the anesthesia machine as well as the total gas flows delivered to the patient circuit. When the flow control valve is opened, the gas enters at the bottom and flows up the tube, elevating the indicator. The indicator floats freely at a point where the downward force on it by gravity equals the upward force caused by gas molecules hitting the bottom of the indicator. As the gas flow increases, the number of molecules hitting the indicator increases. Hence the indicator rises as the force acting on it from the flow of gas is more than that of gravity. As the indicator rises up the tube, the gap around the bobbin increases, which allows more and more gas to flow around it. Flow is a volume or amount of a fluid, gas or liquid passing a set point per unit time. It is usually measured in liters per minute. Pressure difference is the driving force that makes fluid to flow. As the fluid flows through the tube, there is a resistance between the fluid and the vessel wall that opposes the flow. This relationship is like Ohm's law, where flow is determined by pressure difference between the two ends of the tube and resistance. Resistance is further dependent on viscosity of the fluid, length of the tube and the radius or diameter of the tube. This relationship is explained by Hagen-Poiseuille's equation. Fluid flow can be either laminar or turbulent. Laminar flow is the movement of fluid particles along well-defined paths or streamlines, where all the streamlines are straight and parallel. Viscosity is the determining factor for laminar flow. Turbulent flow is defined as the flow in which the fluid particles move in a zigzag way. It is often present where there is a sharp bend or some other irregularity which may cause local increase in velocity. Density is the determining factor for turbulent flow. The Reynolds number is a dimensionless number that represents the ratio of the inertial force and the viscous force of a fluid. It determines whether the flow of the fluid will be laminar or turbulent. A low Reynolds number of less than 2000 indicates laminar flow, while a high Reynolds number of 2000 and more signifies turbulent flow. The rate of flow through the flowmeter tube depends on the pressure drop across the tube, weight of float or cross-sectional area, size of annular orifice, and the physical properties of the gas. As the bobbin rises, there is an increase in the area of the annular orifice. This reduces the resistance to the flow, resulting in increased flow. Applying Reynolds' formula, the increased flow leads to increase in turbulence of the flow. It should also be noted that since the flows are turbulent at higher flow rates, density of the gas is important. At lower flow rate, the Reynolds number is low and the flow is laminar, and viscosity plays an important role in determining flow. Graham's law for turbulent flow states that the flow rate is directly proportional to square root of pressure gradient on either side of the tube and inversely proportional to square root of density of the fluid. Flowmeter are calibrated in liters per min. For flows less than 1 liter per minute, milliliter or decimal fractions of a liter per minute with a 0 before the decimal point is used. They are calibrated at atmospheric pressure and room temperature based on physical properties of individual gases. Changes in temperature and pressure affect density and viscosity of gas and affect flowmeter accuracy. At low flow rate, when the flow is laminar, Hagen-Poiseuille's law applies, where flow is directly proportional to the pressure difference between the two ends of the tube. As flow changes from laminar to turbulent within the flowmeter, the flow becomes proportional to the square root of pressure, and hence the graduations on the flowmeters are not uniform. There may be 1 or 2 rotometers for each gas. Single flowmeter layout is the safest but less precise for low flows. If 2 are present for any gas, the first permits accurate measurement of low flows, usually up to 1 liter per minute, and the other, of flows up to 10 to 12 liters per minute. In such a case, the tubes may be arranged either in parallel or in series. In parallel arrangement, 2 flow indicator assemblies with a flow control valve and control knob for each assembly is used. The total flow of the gas to the common manifold is the sum of the flows on both flow indicators. It is not presently available because of accidental use of a low-flow oxygen flow indicator when a high flow is intended. Series arrangement has one flow control valve for the two flow indicator tubes. Gas from the flow control valve first passes through a tube calibrated up to 1 liter per minute, then passes to a second tube that is calibrated for higher flows. Total flow is not the sum of the two tubes but the one shown in the higher flow tube. Series arrangement increase accuracy at all flow rates. The oxygen flowmeter is positioned on the right side or most distally of the rotometer bank, downstream from the other flowmeters and closest to the common gas outlet. In the event of a leak in one of the other flowmeter tubes, this position is the one least likely to result in a hypoxic mixture. In A and B, a hypoxic mixture can result because a substantial portion of oxygen flow passes through the leak, and all nitrous oxide is directed to the common gas outlet. The configuration in C and D has oxygen located downstream which prevents hypoxic mixture in gas outlet. However, a leak in the oxygen flowmeter tube can cause a hypoxic mixture, even when oxygen is located in the downstream position. Changes in temperature and pressure alter both viscosity and density of gases, thereby affecting accuracy of the indicator on the flowmeters. Temperature effects are slight and do not cause significant changes. When the anesthesia machines are used at high altitudes, since the density of the gases decreases, when higher flows are set in the flow meters, actual flow of gases will be higher than the set flows, as flow is inversely proportional to the square root of density as per Graham's law discussed earlier. The opposite will occur under hyperbaric conditions. In machines without an outlet check valve, if pressure at the common gas outlet increases, this is transmitted back to the flow meters. Compressing the gas above the float. Pressure above the indicator rises, forcing the float down, causing the flowmeter to be read lower than the actual gas flow rate. Static electricity causes the float to stick to the side of the tube, causing reading inaccuracy. These electrostatic charges are negligible as long as the float rotates freely. The float may adhere to the stop at the top of the tube even if no gas is flowing. The float may disappear from view if the float is broken. There are systems designed to protect against the delivery of hypoxic mixture at the flowmeter level. Machine safety standards require mandatory minimum oxygen flow of 50 to 250 milliliters per minute before other gas will flow. Some machines activate an alarm if oxygen flow falls below a certain limit. In modern anesthesia machines, nitrous oxide and oxygen flow controls are physically interlinked so that a fresh gas mixture containing at least 25% oxygen is delivered at the flow meters when only nitrous oxide and oxygen are used. Datex Omeda uses a mechanical linkage called Link 25. North American Draeger machine has pneumatic interlink called Sensitive Oxygen Ratio Controller. The Link 25 system operates with two control knobs, one for nitrous oxide and the other for oxygen, connected by a chain. The nitrous oxide knob has a gear with 14 teeth, while the oxygen knob has a gear with 28 teeth. For every 2 turns of the nitrous oxide knob, the oxygen knob completes 1 rotation due to the gear size difference. This design allows independent adjustment of each knob while ensuring a minimum oxygen to nitrous oxide ratio of 1:3. If the nitrous oxide flow exceeds 75%, the oxygen knob automatically adjusts to increase oxygen flow, maintaining a 25% oxygen concentration. Similarly, a significant decrease in oxygen flow results in a proportional reduction in nitrous oxide flow. The sensitive oxygen ratio controller is a pneumatic master and slave system designed to maintain a minimum 25% oxygen concentration. It consists of an oxygen chamber or master control, a nitrous oxide chamber, and a nitrous oxide slave control valve, all connected by a movable horizontal shaft. Oxygen and nitrous oxide flow into the system via flow meters with resistors creating back pressures toward the chambers. These pressures affect rubber diaphragms attached to the horizontal shaft. The shaft's movement regulates the nitrous oxide slave control valve, controlling the flow of nitrous oxide through its flow control valve. In the lower diagram, when the back pressure on the oxygen diaphragm exceeds that of nitrous oxide, the shaft moves left, opening the nitrous oxide valve. In contrast, insufficient oxygen back pressure closes the nitrous oxide valve in the upper diagram. Machines equipped with proportioning systems can still deliver a hypoxic mixture under the following conditions. Wrong supply gas in oxygen pipeline or cylinder. Defective pneumatic or mechanical components. Leaks downstream of flow control valves. Inert gas administration like helium and carbon dioxide. Proportioning systems generally link only nitrous oxide and oxygen. So use of an oxygen analyzer is mandatory if the operator uses a third inert gas. Unidirectional check valve is present on some machines between the vaporizers and common gas outlet upstream of where oxygen flush flow joins the fresh gas flow. The functioning of check valve is as same as the one used in hanger yoke check valve of high-pressure system discussed earlier. Positive pressure ventilation and the use of oxygen flush can cause backflow of the gas to the vaporizers and flow meters. This backflow can cause pumping effect and if not prevented could cause increased vaporizer output. Pressure increase can also cause inaccurate flow indicator readings. The purpose of the outlet check valve is to prevent reverse gas flow. Newer machines like Draeger are equipped with vaporizers that incorporate a baffle system and specially designed manifold to prevent pumping effect, making an outlet check valve unnecessary. The pressure relief valve is located on the back bar of the machine, downstream of the vaporizers or near the common gas outlet. Its purpose is to prevent high pressure from moving into the machine or from the machine to the patient. It is also known as a pop-off valve and operates through a spring-loaded mechanism attached to a disc, which closes the valve below the set pressure. As the pressure within the system increases, the spring is pushed upward, releasing the excess gas. Typically, the pressure relief valve opens at 35 kPa or 5 psi. The vaporizer mounting device is between a flow meter and a common gas outlet. It is permanently mounted. Vaporizers and the flow meters are connected to each other and then bolted with back bar. Common gas outlet receives all gases and vapors from the machine and delivers the mixture to the breathing system. This connects to the anesthetic breathing circuit to deliver the combined product of gases and anesthetic agent to the patient. The pressure delivered at outlet is 5 to 8 psi.